My name's Steve. Thanks for coming. Talk about Testable by Design by me. This is me, I'm Steve. You can find me here, and you're going to hear, I think, a few speakers mention that imposter syndrome is for everyone. Everybody gets nervous. But I'm here to say that I'm a real imposter. Because if you know me at all, to the extent that I am recognizable, you most likely know that I write about C# quite a lot. But I do have a little bit of background in C++, and been known to give a talk or two, but I've got a couple of books on C#, but they weren't really useful for preparing this talk, because this talk is kind of a bit more C++-y, honestly. What was more useful to preparing this talk was this book, written by my wife, which I'm here to plug, but I did refer to this quite a lot because I'm coming back to C++ from quite a long time ago, nearly 10 years, and I was interested to pick up modern features in more modern releases of C++, and this book genuinely, I'm biased, I know, but was genuinely useful. Because it is a little bit, when you're coming from around about C++ 14 to introducing some C++ 23 features, but mostly C++ 20, it's a little bit like learning a new language. As long as you're kind of familiar with other languages that are similar, C#, for example. So, yeah, that was a book that helped me do this. The talk itself really is, it's not really a C++ talk at all, although the examples are in C++. And I want to expose some of those more modern features, but it's not really a glossary of terms in C++ 20 or 23. It's more about how I thought that those features helped me express my design more clearly, more succinctly, more simply. So this is what we're going to talk about. It is a talk about design rather than C++ technique. But we're going to just mention a few of these along the way. Tell, don't ask, the idea of co-locating data and behavior. Parameterize from above, the idea of passing in dependencies rather than reaching out for them or using global variables. We're going to look at some, what I think about as slightly below the fold features, or that have either dropped off the top headline C++ features. Things like standard chrono, CTAD, smart pointers, initializers, concepts. And my tech platform for this was kind of GCC around about 13 or 14, so pretty modern, not necessarily right at the cutting edge. And mostly C++ 20, or up to C++ 20. I think there might be a couple of 23 things, which I pull out in comments. Keep your eyes open for those. Despite the title of the talk, Testable by Design, this isn't a TDD talk either. But we are going to mention TDD a little bit because it's relevant. But I'm not really a TDD evangelist, although it's my personal preference for designing my own software. I think that there are alternatives that are, TDD is not the one true way. But it's relevant to some of this, because designing software so that it's flexible enough, so that it's easily tested, is something that TDD can help with. Also, on the other side of that, we're going to pull in a couple of what I think of as software architects' favorite terms, ubiquitous language, if you've come across that, which is a term that comes from domain-driven design. And there are some elements of this talk that slightly dip a toe into that water as well. But this isn't a DDD talk either. What we are going to talk about is a simple heating controller. It might be an embedded system, it might be within a game, for example, or anything like that. It needs to be an example that I think is realistic enough that we can expose some of the design pinch points, but that's simple enough that we can fit it in a 60-minute talk. So there are some basic requirements up front that we know about, and some constraints. So a heating controller, you might want to turn heating on or off at certain times of day, so you need to have a concept of time when you're designing a system. And it needs a facility to read what the current temperature is. So there is some environmental constraint there, and that's via a third-party API, so something that you're being given by somebody else. You may have no control over it whatsoever. And then the switch to actually turn it on and off. And again, a third-party API, something over which you may have no control. So that's the basic outline that we're going to explore. And here's a bit of pseudocode. If the start time, or if the time now is between the start time that you've set and the end time that you've set, you read the sensor, and if the temperature needs to come on, if the heating needs to come on, you turn it on. And if the temperature is already at a nice, comfortable level, you turn it off. So it's a pretty straightforward system, but there are some unknowns to this. Your third-party APIs might not be ready for a number of reasons. The hardware might not have been built yet, so nobody knows how it works. Or you haven't decided on what library you're going to use. There might be options in that space. It's being developed elsewhere in the company, perhaps, and they've not started it yet, or not finished it yet, or they don't know what to do. Well, a third party, for the same reasons. This kind of uncertainty is often seen as a blocker. Well, we don't know what we're going to do, so we're not going to do anything. And this is kind of where TDD is relevant, because this kind of uncertainty, the same idea of where do you begin writing tests for code that you don't know what it's going to look like. Well, that's part of what we're going to explore. Kevin Henney, whose name I hope is familiar to many of you here, has spoken about this lots of times in the past. He's certainly the person that I learned this approach to software design from. How do I design a system so that the choice between option A or option B is less significant? Ideally, so that it's not significant at all. So he gave a talk, and he's written several times on, but use uncertainty as a driver is a good search term for this. The idea being that you need to do some design up front, but some of the details might be filled in later, and you can make your design malleable enough so that those details have little impact on the final system. So you defer decisions if it's possible to do so, or if it's necessary, because you can't make them now. And it's fine to get it wrong. So some design up front, yes. If you get it wrong, you can revisit it later. Most doors are not one way. If you make a decision now that you cannot defer, and it turns out that your constraints or the requirements on your third-party API change, then it's usually possible, if you do it soon enough in the process, to choose a different door, if you like. But you still need to identify where the core of your uncertainty is. So let's just take a breath. We've got some very distinct concerns that we want to address in our heating controller system. So we need to step back and consider how do we separate those concerns out? So turning the heating on and off is something that actually hits the hardware. That's going to be a hardware switch of some kind if we're talking about an embedded style system, right? Deciding when to turn it on or off is an unrelated or almost orthogonal concept. So it's up to us, and we can address them separately. So we'll do the easy one first, which is the heating system. Because this is easy, because we don't know what our third-party API is. So we need to use that uncertainty to fuel the imagination of the API that we'd like to use. Spoonerism. So we want the API to be as simple as possible. If you're not familiar with the term spoonerism, it's when somebody standing in front of public speaking like me mixes their words up, or in this case, the letters in an acronym. to hilarious results often. Sorry, bit of a side thing. We want to use the design, or we like to design an API that's simple and that's obvious. And this seems pretty simple and obvious to me. I hope you agree that if we've got a heating system that we need to turn on and off, then having some kind of base class that defines defines the interface to how we switch on and off seems like a logical first step. Because it's a base class, we can inherit it later and fill in those details for a specific implementation. We might have to refactor it later to account for changes, but that's fine. As a first step, it's good. Now, C++, this is where my C# history comes in. C++ doesn't have a true interface type. Interfaces in C# and in Java are slightly different in some very important respects. Principally, that an interface in Java or C# is never virtual. We don't have that option in C++, so we have a pure virtual base class, which is its nearest analog to those ideas. But the purpose is that this base class has no implementation. It purely defines what the interface needs to look like. And the virtual destructor is mandatory. I can't remember whether it's UB or malformed if you don't have it in a virtual base class. Somebody can enlighten me later. But the point is you have to have it or things go wrong. If we have a destructor, then we have some other things to consider. The rule of 5. So this was something that was kind of new to me. So move semantics was something that I was familiar with, but I wasn't really using C++ in anger even 10 years ago. So I was quite familiar with the rule of 3, that if you define a destructor, then you probably need a copy constructor and an assignment. Move semantics adds move constructor and move assignment to those things. But we're doing these just as the default. Now, that at least takes some of the syntax away, and that was new to me when doing this, is where previously they would have to be empty. Lots of extra braces. Equals default is much neater. Because we're using the default, you might argue, well, it's the default, you can leave them out. But I prefer explicit to implicit, just to say that we have considered these things and actively decided that the defaults are good enough for our base class. And, well, we probably need a default constructor as well. Since we define copy and move, so we've got a rule of 6. And this defines the basic interface to our base class. With that in place, we can write our own implementation that we're going to use to test, firstly, whether the API we've designed is useful enough to do what we need. So we inherit from the base class with a fake. You make it as simple as you can, but you don't want to test this fake object. This is literally something that you're going to plug into tests to be a dependency elsewhere. But don't get hung up on the terminology around fakes versus mocks versus stunt doubles. They're all basically the same idea. Just do the simple thing so that you can write a test around it. We don't need to redefine all of the destructor, the copy constructor, the move assignment, all of that. The base class has the right semantics. All of the correct semantics are inherited from the base class, and that will probably be true in most cases by our real implementation. But we'll address that later because we haven't got one yet. So with that in place, we can start thinking about what the heating controller needs to look like. And this is something that we can implement properly. If you remember from the beginning, the controller is the thing that tells you when you're going to switch on and off. So it's time to address the time. This is where chrono comes into the matter. And we're going to take it literally. We're going to call the controller controller. There's probably a better name, but it's obvious enough for now. This is something that we're going to hang our business logic on. This is the heart of the system. And it's an active object. So an active object is something that encapsulates an action. It does stuff. You tell it to do the thing it's supposed to do. In this case, activate. We don't ask for properties and do the action elsewhere. So we don't ask the controller, is it time to turn the heating on? Or is it time to turn it off? We say, just do it, activate. And the semantics of the activate method are to determine whether we're in the time window. And if we are within the time window, we turn it on. Otherwise, we turn it off. It's far from perfect for lots of reasons that you've probably spotted already. But we can write a test for this. And so this is why this isn't a TDD talk, because otherwise I would have written the test first. But we could have written the test first. So we're just using, or I'm just using Google Test Framework for this. But the point here, you can use whatever test framework you like, it doesn't matter. That's unimportant for this. What is important is that we're using the test as a kind of a pretend main, so that we've got a way of scaffolding up the pieces that we've written so far, and then we can run it. Instead of running an application or running an executable, we're just running a test. But the test contains what you probably expect to find in main. So we're using unique pointer for the system because that's what it is. Because we don't care at this point that whether it's a fake heating or whether it's going via the base class. But that is obviously going to become relevant later. But a controller is an observer of the heating system. It doesn't own the lifetime as such. So whether we don't pass in the unique pointer to controller at the moment. We're passing in the raw pointer because it's an observer. Now, there is an argument around lifetime where if the thing that you're passing the pointer to has no interest in the lifetime, and that is certainly true of controller, it's not sharing the lifetime. It doesn't manipulate it in any way. It doesn't just try to destroy it if it's the last thing referencing it. The lifetime of the heater is the outer scope. There are alternatives, which we're going to look at, but I kind of want to float that one up. About raw pointers have taken a very great deal of flack over the last mumble years. But sometimes they are the lightweight option. And then we've got a duration type somewhere. Possibly not on this slide. The problem here is, does this test pass or not? And the answer is, well, it might. Depends what time of day you run it. Because we'd encoded the idea of now into the controller. If I go back. It's here. We determine what the current time is inside the controller. So when we run the test, we've just got to make sure that we've set up the correct start and end time so that now falls between it so that we can test the outcome. Activate is reaching out for now. It's doing this ask, not asking the global environment, effectively, for a value, rather than telling it what to do. So, okay, we need a way to keep track of time in a different way. So we create a helper type. Some helper types are just helpful. They just are. A time of day is really just a duration since midnight for any given day, for the purposes of this talk. So the type names help us codify our intent. A time of day is a duration. We've got a wall clock time, which represents a particular clock in standard chrono terminology. And those two things together allow us to create this time window type, where we can construct a time window with a time of day for the start and end that we want our window to represent. And then we can ask it whether we're in the window by passing in what we think of as the time for now. So that means that we can pass in any time we like. This is not an active object. It doesn't do anything. It's specifically something we're going to ask for a property of, but it's a semantic property of it, whether we're in the window or not. So that contrasts with the controller, which was an active object. So now we can make a more testable controller that doesn't embed the idea of name. And here we are substituting raw pointers for shared pointers. Sometimes the idea that having raw pointers hanging around introduces some ambiguity in the code. Whoever's reading the code has to look at it and just possibly make sure that it's not really doing anything with lifetime. So using shared pointer in this context probably helps the reader of the code because they don't have to think about that. They can notice that it's a shared pointer and just move on. So the implicit lifetime management is encoded in the signature of the constructor. And we pass in, it doesn't need to be anything special. It's just a const ref to a timer. We could have passed in a copy. It probably wouldn't have made any difference in performance. What has made a difference is that we've reduced our constructor parameters and the type names are more meaningful. So anybody reading the signature of this, hopefully, it's reasonably obvious what this is supposed to be doing. And then we've changed the signature of activate to pass in a wall clock time. We call it now because that's what it's going to be in real life, probably. But it's as good a name as any. The important point is that we're passing it in, rather than the controller reaching out for a global variable. So we remove a dependency on the actual time. This is an example of dependency injection. If that's a term that you've encountered a lot and think that sounds complicated, it's not. This is about as simple a dependency injection as you can get. The idea that we're passing in a parameter to a method rather than it reaching out for it. So here's our test. We can't convert from a unique pointer to a shared pointer, so we just make a shared. Introducing shared pointer at this level means that we go shared all the way down, or resort to raw pointers. There is no conversion between unique and shared pointer, so you make your decision, and well, you make your bed and you lie in it, basically. In a system like this, it's probably not an important decision. But the point of this is the task pass is all the time because we pass in the time for now. So we can use a relevant time window and just pass in a time that's between those times, and we think that asking for the current status should come back as true because the time that we pass in is between the start and the end time that we constructed the time window with. And it does, all good. In real life, or in real code, rather than creating a new time, obviously we would probably just pass in now, the global variable. But we don't need to. We've removed our dependency on that. We're testing the outcome, not the implementation. If you take one thing away from this talk only, that's the one thing. Testing for outcomes makes your tests much less brittle, much less subject to the need to change when you refactor code later. That's not a rabbit hole we're going to explore very deeply in this talk. But I do want to call that one out, because outcomes that's the behavior of your system, rather than how it's implemented under the hood. The more tightly coupled you make your tests to the implementation, the more likely you're going to need to change the tests when you change the code. And the reverse is true. Testing for outcomes. The outcomes are normally factors of your design and don't change in significant ways. They might change in the way that they're represented, which might well require a change to the tests. But those changes are going to be very small, not structural. TDD can suffer from over-testing implementation detail because writing the test first, naturally, as programmers, we're thinking about how we're going to implement a particular feature. And it's natural for a test that's written up front to, even by accident, take that into account. So a little bit of design up front can help to alleviate that. But it is one reason why, in the test cycle that TDD describes of red, green, refactor, that's why refactor is so important. And you refactor your tests so that they are more dependent on outcomes than they are on implementation. That's probably the last time I'm going to mention TDD, I think. I'm not promising anything right now. So we now have a controller that we can test in a reasonable way. We have a base class for a heating system that we can abstract away the dependency on the hardware from. Well, we're still not done. We've only done half the requirements. We need to figure out what the current temperature is. So again, we can roughly sketch out what we want, a way to set the target temperature so that the controller knows whether to go on or off if it's within the time window. So we read the temperature and pass it into the controller. Okay, well, we could do that. Here we've just got a simple property setter that's, okay, it's taking a raw number. I could have come up with a whole new type to represent temperature. Let's just assume, for brevity, that that's 25 degrees Celsius. I know I've made a big thing about the type names being meaningful, and this is one place where that would have probably helped. But even leaving that aside, we can probably do better in the design. What about the idea of a sensor type? If we abstract away the idea of a sensor that knows about temperature, then we again keep our different concerns of the system separate from each other. And we can use it as a way of managing dependencies differently. Now, the idea of coming up with another abstraction, a sensor, this isn't something we anticipated up front. In pretend, I know, but it wasn't mentioned at the top of the talk. But it's kind of an example of emergent design. So we might have a very simple API, again, provided by a third party, that we want to abstract the idea away. So we assume, again, that it's reading degree C. But we can use the sensor as a way of also controlling the heating system. But rather than having a single controller that knows about sensors, it knows about time, it knows about the heating system, we use a different kind of design, where our controller now becomes a thermostat. And all it cares about is the time. And a heating, which might be a fake heating, is the thing that turns it on and off. The thermostat is a heating system because it has, not just because it has the same API, it is part of that interface. It matches the interface. If the temperature is less than the target, then we switch on, otherwise we do nothing. And we pass on the switch on, if necessary, to either the real heating system or the fake heating system for a test. So this is kind of a condition filter. So here's a simple implementation. Again, we don't have any external dependencies other than our abstract base class for the heating system itself. And it takes a reference to that in its constructor. So here we've got a type that inherits from a heating system that also takes another heating system as a dependency. Just want to call that out. Just bear that in mind. We also pass in a target temperature. So that's the 25 that we were looking at earlier. and a function that takes no parameters, returns an int, that reads a sensor. And then somewhere, maybe I haven't shown it, switch on and switch off are just going to forward on to the heater if the condition is met on the temperature. So a quick reminder of our original interface. This corresponds exactly to that function parameter for read up there. And the test shows how we, again, pretend main, these things as we would kind of show them in a real main. How to use the system. We create a heater, which is just a fake heating. We pass it into the thermostat, which is also, we're calling make shared for the thermostat, with that 25 again. And our hard-coded sensor, which is just a global or block scope simple function that returns a number. For the purposes of the test, it's a good enough number. All we need to know is whether, if the temperature that we pass into the thermostat constructor is above the sensor reading, then it will turn on, and we assert it. Couldn't be simpler. So now we can update our original controller to take that into account. Reading the current temperature is encapsulated in the thermostat. We now pass, have I got this right? The thermostat into the controller, not the fake heating. The controller only cares about the time. And again, we're using the same hard-coded sensor, our same 25 for what we think our limit wants to be for the test. If the time is within the window, the filter drops through to the thermostat. Well, that's interesting. We've got a controller that is controlling the heating system based on time, and a thermostat that's controlling a heating system based on temperature. It's almost like they're related in some way. A pattern is emerging. In fact, perhaps we can use the same interface to manage time and temperature and heating controller. So we have a common base class, a heating system, which you can turn on, turn off, ask for its current status. We now have a timer activator instead of a controller. Activator, that's interesting. That's something that we're going to revisit. So a timer activator, which cares about the time of day. If the current time is within the window, then it passes on to the thermostat, which is the thing that's concerned with whatever the current temperature is. And if it matches that filter, then it goes off to the fake heating system to actually turn it on or off. We can extend this idea. So here's a slightly different implementation. Previously, we used a standard function, so using type erasure to abstract away the idea of our external API. Instead of using standard function, we can make this a template and make it a clever template by using concept to say that we're using standard invocable. So whatever we use for the function type, notice the capital F for function, must be an invocable thing. So whether it's a global method or a lambda or something with their function call operator overloaded with the right signature. That's a C++20 thing. But I'm sure all of you are more familiar with that than I am. We still pass in a shared pointer to the heater, and to the time window, but instead of taking a standard function, we're now passing in whatever the template parameter is represented by the concept function. Switching to a template brings some compromise. We now have to implement all of this inline in some way, whether that's directly within the class declaration or whether it's in a separate file that's included, but it still has to be inline. But it is faster than using standard function because we're not relying on type eraser. Also, perhaps it's a good time to rename heating system as the base class heating system as activator or heating activator, because that, I don't think I did actually in the slides, but I do want to pull that out. It does replace the controller. So we've got yet another test, slightly more sophisticated this time. Again, making a fake heating object, but we've got a inline declared lambda to represent the get the time for now, and another one for reading the sensor, and then we can pass those in to the timer activator and the therm activator, respectively. And then, now when we call switch on, we should be able to determine that the current status is in fact on because the time window and the temperatures match, blah, blah, blah. Each part of the chain calls and depends on the next dependency. So notice the order of construction here. We've got creating the heating system, the thing that actually would actually touch the hardware, although we're faking that out. When we create a timer activator, that's the thing that is going to talk to that if the time window is in place. The thermostat activator takes the timer in its constructor. So the thermostat activator, that's the thing that does, sorry. Have I got this terminology the right way around? I can't remember where I'm being consistent. Therm activator cares about reading the temperature, but we're passing in a timer. Oh no, we're passing in the read sensor, that's correct. So that is going to forward to the timer if the temperature is below what we want. The timer is going to pass on to the heating if the time is what we want. We've now got, because fake heating isn't a class template, we can use make shared for that. But we can't use make shared to create timer activator and therm activator. Somebody else might be able to help me with this, because I'm not entirely sure why. But we can't rely on CTAD, compile template argument deduction, to do this by using make shared. That is what we're relying on elsewhere. This becomes a bit more important later. But we can just create a constructor shared pointer by passing in the template argument for those two things. It's not truly horrible. It's not quite as nice as make shared, but that's one of the compromises with switching to a template. Oh, more importantly, timer and stat, or the timer activator and therm activator types, are testable independently of each other and everything else. We can write independent tests. Extending the idea further, could we override the heating in a different way to say, I want to be able to push a button just to say, turn it on for an extra hour, or just turn it on until the next time it would have otherwise turned itself off, or just turn it off? Well, we can. We can add a new activator. Again, using the invocable, so template using a concept. But this time we've got something different in our API. It's extending the base class API with this override. That's a type-specific implementation. But again, in the constructor, we just need a reference to the next filter in the chain so that we can plug this in at any point. I mean, there's a logical place where this would plug in. And we also need a way to get now, the same as the timer activator. But okay, we can arrange for those things to happen. But this slightly changes the shape of our design. But it's not completely different. We've still got a the idea of a falling through depending on a condition. And if you're familiar with the gang of four design patterns, this is more than just reminiscent of chain of responsibility. And the idea of chain of responsibility is that you pass a message into the first object in the chain, and if it can handle it, it does, otherwise it passes it on to the next. Well, that's very, very like this. Now, there is a variant of this that will filter requests, or that will pass a request on regardless. There are some design patterns that are a slightly different shape to this, or rather that are the same shape as this, in terms of the kind of the mock UML that I'm using here. But they have different motivations. So whether this really is chain of responsibility, it's not exactly chain of responsibility as the gang of four describe it. But the motivation for it matches exactly. So chain of responsibility is a good enough way to describe it. It relies on virtual dispatch because each object takes a reference to the next object in the chain, and it doesn't know the details of what that are. It doesn't know what implementation is. It's taking a reference to the base class. It's not likely to impact performance by much. I doubt that we're going to be turning the heating on and off millions of times a second. Hopefully not. It does mean that you couldn't use one of the alternatives like standard variant for this, because variant requires a fully constructed object for each of its types. So you couldn't pass in the variant type to the constructor of each thing, because you couldn't have created it yet. However, the virtual dispatch does have the advantage of being clear. It's reasonably obvious what's going on. We can draw what is not a very complicated picture to describe everything. So clarity first. There is more difficulty going on here because the decision to go with templates rather than standard function now comes to bite us on the unmentionables a bit. Our override activator has some type-specific behavior, the override, which means we can't use a reference to the base class in our test or in our real code. We need a reference to the real thing. But declaring the shared pointer means that we need the type argument for the function concept. And we've used a lambda here, which is unnameable. So that fails to compile. The override activator constructor, we'd have to put template arguments in, and we can't. Well, we could kind of rewind and take out the template and go back to standard function or similar kind of way of handling that. Or we can introduce another pattern. Also described in the gang of four, but this is a very, very simple example of it. The factory method, where we sprinkle a little bit of template magic, which helps the template argument deduction. It's kind of reminiscent, if anybody's familiar with Andrei Alexandrescu's modern C++ design, the name of which now seems a little anachronistic. He was talking about policies in the same way in that. And it's reminiscent of that. This is not the same thing. This is merely using it as a mechanism to deduce the template arguments rather than having to specify them exactly. And we can move things around rather than copying them and make use of all of the funky C++ stuff. But the point is, it just makes using it a little bit easier. We've now got, instead of make shared, we've got make activator, and the magic happens in the template at the top. So the invocable concept is extra useful here to encode the intent, Because otherwise make activated would just be an open, you could make it with anything, and then it would fail much later down the line. And the compile time errors would probably be incomprehensible. They would require a little bit of detective work. Using standard invocable here, the compiler can absolutely pinpoint where your problem is. It will be at the call site. So it's useful for that as well. So concepts is, it's not just about making compile time errors more readable, but that is still, it's a really good use case. So that's kind of about it, really. Key thing about this is that we let uncertainty inform the design, not block it. Rather than waiting for our third-party API to become concrete so that we knew exactly what was going on, we had no idea what it was going to be, so we made it up on the spot. It would probably not be very far from the real thing. If it was different to the real thing, there are approaches we can take to adapt one thing to another, but it would have required very little refactoring, I suspect. So own your own types and give them names. Own the names. Here's something that's from domain-driven design, but we don't have to call it that. It's just a useful concept to have a language within your team so that you all know what you're talking about. When you talk about having a sensor or a time window, or even a time of day, which was just effectively a type def in old world language. It names the thing that you mean that you're talking about. And it helps to guide the conversations so that people know what you're referring to. Broadly speaking, tell objects what to do and how to do it, rather than ask them what you need to do. Tell, don't ask is about putting data and behavior that are related together, encapsulation. The idea of asking something for a property that you're going to use elsewhere to perform an action, that's an obvious case to encapsulate in a single place into an active object, if that's what it's going to be. There are still going to be helper objects, like our time window, where you just need to construct one and ask it later. And that's just a helper object. But knowing the difference between something that needs to be a controller type active object or something that is a passive helper thing is important in design. And it helps you to name things appropriately as well. And then pass dependencies in instead of wiring them and reaching out for now is reaching out for now is a classic example that is a barrier to writing tests. It's not just a barrier to writing tests, it's a barrier to system malleability, of being able to refactor later and for unexpected errors when you least expect them. But extensible design is more than object orientation, but that is what we're talking about here. This is reasonably obviously, I think. This has been an example of classic OO, where we're inheriting from a pure virtual base, calling virtual methods. There's still a place for that. There are some places where you can't avoid it if you want to keep your design sane. And OO is more than extensible design. Giving objects names is the most fundamental thing about it. So that's it for the main part of the talk. And you can find me in all of these places. But we've got a bit over 10 minutes left. So I'm going to ask now if there are any questions so far, but I have some bonus material that is all related to the talk. The question over here.
Hi. First of all, great talk. Very, very good points about testable design. Big fan. I have one question. Maybe I missed it and haven't quite understood it, and that is, why were there shared pointers involved at all? Because it seemed to me like the lifetime and ownership was pretty linear and one way. So was it just something that you wanted to show how that works with shared pointers, or was there an actual need to use shared pointers that I missed?
It wasn't actually required at that point, but it avoided the need to pass in a raw pointer to the controller as a reference to the base class. Because we couldn't, passing in a unique pointer has the wrong semantics at that point, because the heating object still needs to be alive, because we're going to ask it questions. Let me see if I can find a slide. This is a good enough example of it. The heater, if this were a unique pointer, and we passed it to here as a unique pointer, that variable goes away. But we're using it in the assertion. So it either has to be shared pointer or raw pointer.
I didn't think of replacing a shared pointer with a unique pointer. Of course, if you move it, then it goes away, it's clear. But I was thinking, you'd have just created the fake heating on the stack and then pass it on as a simple reference into the thermostat here, and then pass the thermostat into the controller as a reference again. And the lifetimes, I think, would have worked out. So that was actually my question.
Hold that thought. That's bonus material number 2.
Ah.
Hey, hi. Thank you for the talk. One question which I have, like you are inheriting from the base class, and the same thing you have it in a constructor as well, in one of the public heating.
Yeah.
Why is like derived class will already have the instance of the base, right? So why we are specifically passing them?
Because they're different objects. So I think, hopefully this describes it well enough. They all inherit from the common base class. That common base class is what allows the filter, when the timer activator wants to turn the next thing on, it needs a reference to the next thing in the chain. And it could either have a reference to the actual thing, where it would then be encoding the exact order that those have to be in, or it can take a reference to the base class, so it can be any one of these. So it's just a point, it's a point of flexibility in the design, if you like. Does that make sense?
Yeah, thank you.
Great.
I have some questions from online. So Stefano Cagliazza asked, what about using concepts to define interface without relying on virtual interfaces?
It's a great question. Partly, I think my experience with concepts is not deep enough to understand all of how that would work. But also, I think that the limitations I explained about using the concepts, almost, I couldn't see how to use them without the idea of templates, which introduced those other limitations that I explained. So the combination of the two, I think, is the most flexible design. But I could be wrong, because it's design. You can disagree.
Thank you.
So, my question, so first of all, thank you for the talk. My question would be, you had this real nice assumption, you have some third-party API, and now you discover some really weird thing we have no influence on. For example, at midnight I have to call switch on twice. How would you approach such a thing? Because, I don't know, it took us 3 days of debugging.
Yeah, and so you're never going to avoid the debugging to identify it.
Yeah.
But once you've identified it, that is behavior that you can put into your real implementation. And having put it there, you can also separate out a separate behavioral test to make sure that you're doing it, right? But that's where the idea of having the common base class as a seam that you can change your implementation becomes absolutely valuable, because you can write a different implementation to cope with that very, or weirdnesses like that.
Yeah.
And yeah, we've all seen them.
Thank you.
Okay, I think that there isn't enough time to do the bonus material, unfortunately, but I was going to talk a little bit about the performance between standard function and the templated lambda, and also about RVO, which was related to your question. Come and find me afterwards. And anybody else that's interested in that, if you remember the question, it was about rather than passing in a shared pointer to a constructor parameter, pass in an ordinary reference. And I'll talk about that, but come and find me afterwards and I'll spend a little bit of time going through it. Brilliant. Thank you very much.